Alright, moving on to problem 3. This is a low-pass filter. And I am going to attenuate an 80 kilohertz sine wave by 40 decibels. And I'm given the value of R. And I want to know the value of C. So the challenge of this problem is to find what the 3 dB point of this filter is. Once you know that, then you know that you can find the values of the components from this formula. 2 pi times R times C. So if I find this, then I have a rather simple formula to apply to get the unknown part. Depending on which exam you got, you had different frequencies, you had different styles of filters, or you had either R or C, depending on your particulars. Now, the easiest way to approach this problem is to remember the trick that is essentially suggested by this equation here. I know that I'm going to go 20 decibels every time the logarithm of this quantity goes by 1 or 2 or 3 or so forth. And that corresponds to a change of a factor of 10, because a logarithm of V out over Vn is going to be a whole number for every factor of 10. A single factor of 10, V out over Vn, is going to be a logarithm of 1. And if V out is smaller than Vn by a factor of 10, the logarithm is minus 1. So I know that I've got 40 decibels implies that I've got 2 decades. And that implies that I need to go from 80 kilohertz, and it's a low-pass filter. Remember, the Bode plot of the low-pass filter looks like this. So I'm out here at 80 kilohertz, and I want to find out what that point is. So I'm going to go down in frequency, first by 1 decade to 8 kilohertz, and then by another decade to 800 hertz. So that's F3dB. So that would basically solve this problem then. So if you've done that, you've saved yourself a lot of work. So if we wanted to find out what that was, I could say that 800 hertz is equal to 1 over 2 pi times R, which is 430 ohms, times my unknown C. And that means that C is equal to 1 over 2 pi times 430 ohms times 800 hertz. And if you calculate this on your calculator, you basically get 0.46 microfarads, which is close enough to 0.47, which is this answer. Now, if you didn't think of this trick, you want to go back to the basics. We can just crank this through by thinking about our complex impedance of this resistance and this capacitance. So, in terms of complex impedance, V out over Vn is going to be equal to, remember, I've got the lower impedance divided by the sum of the upper and the lower. So that's going to be ZC divided by ZR plus ZC. And that is going to be equal to 1 over I omega C divided by R plus 1 over I omega C. Simplifying this a little bit, I get that this is equal to the magnitude of 1 over 1 plus I omega RC. And this is simply equal to 1 over the square root 1 plus omega RC quantity squared. Multiply by the complex conjugate and take the square root is how you find the magnitude. So I can start with this, where this is now my omega that's associated with my 80 kilohertz. And this would be my R and C that are associated with the problem. And I have basically going to make this equal to V out over V in, which I know, since this is 40 dB, that this logarithm of V out over V in is going to be equal to -2. So that means that V out over V in is equal to 1 over 100. So I set these two equal to each other. And I can now solve for omega RC. I plug in the values of omega, I plug in the values of R, and that would give me a value of C. So let's just follow this through. I will have that 100 then is going to be equal to the square root of 1 plus omega RC quantity squared. I can square both sides. I'll have 100 squared is equal to 1 plus omega RC quantity squared. I will then have omega RC quantity squared is going to be equal to 100 squared minus 1, which for all intents and purposes is pretty close to 100 squared. So I'm just going to say that omega RC is equal to 100. And then I can write C is equal to 100 divided by R omega, which is equal to 100 over 2 pi F R. And you can basically see that this 100 and that F, which is 80 kilohertz, gives me the same value for C as this version up here. Okay, that's it.